Diffraction grating. When a wave meets a single slit of a similar gap to the wavelength, we get spreading or diffraction a bit like this. The wave meets the gap and then spreads out as shown. This happens with all waves: water waves, light waves, sound waves. The wave started coming in this direction and is now spreading in these and all other directions. A diffraction grating is simply many gaps like this, one after the other. In fact, a diffraction grating will generally have many thousand of these gaps. If we consider some light meeting a diffraction grating and look at just one angle that the light is diffracted at, which we'll call angle theta, if we now place a line at 90 degrees to this ray, this angle will also be theta. If the distance between the gaps is d, this distance here will now be given by d sine theta. But this distance is the path difference to the screen from this gap and from this gap. If these rays meet to constructively interfere, this path difference must be a complete number of wavelengths. So this distance must also be n lambda, where n will be a whole number and lambda, as usual, is the wavelength of the light. So we've found that this distance here is n lambda, but is also d sine theta. So we can write that n lambda equals d sine theta. You will not be expected to derive this equation, but you will be expected to be able to use it. Let's now look at what happens when light hits a diffraction grating. Here we have a diffraction grating with the slits a distance d apart. A ray of light of wavelength lambda is incident on the diffraction grating. The light that passes straight through will have zero path difference from the many different slits, and so will have zero phase difference, will constructively interfere to produce a bright band. This first central bright band is known as the zero order, or for this n equals 0. The ray that is diffracted up here by an angle theta, at which the path difference from slits is just one complete wavelength, is the first order, and for this n in our equation equals 1. Of course there'll be another first order the other side of the central bright band. At a bigger angle up here there will be the second order. At this angle there will be two complete wavelengths path difference, and n equals 2, with a partner down the other side. 3 wavelengths path difference give us this angle, and n equals 3. There may be more bright bands depending on the distance d of the diffraction grating and the wavelength lambda of the light. We'll look at this in a moment. Looking at this arrangement from a different angle, the ray of light comes up, passes through the diffraction grating. This is the undeflected ray, leading to the central bright band, or the zero order band, where n equals 0. This ray is deflected such that there is one complete wavelength path difference from the light coming from adjacent slits. Here this is the first order, or n equals 1. For this ray there is 2 complete wavelengths path difference, so n equals 2. For this one n equals 3 with 3 complete wavelengths path difference. Of course we have n equals 1, n equals 2, n equals 3 at the other side as well. All these points are where there is a complete number of wavelengths path difference leading to constructive interference, which is seen as bright bands on the screen. Now, we showed earlier that n lambda equals d sine theta, where n is the number of the order, so n equals 1, n equals 2, n equals 3 from the central position, lambda the wavelength of the light, d the distance between slits on the diffraction grating, and theta the angle from the central point. So this angle, for instance, for n equals 1, this angle for n equals 2, and this angle for n equals 3. Looking at this equation, we see that as lambda, the wavelength, gets bigger, sine theta must get bigger, as n and d are fixed, meaning theta gets bigger, so the bright fringes will spread out. As d gets smaller, so the diffraction grating has a smaller gap between the slits, sine theta again will get bigger, meaning theta gets bigger, and again the bright fringes will spread out. Don't forget that sine theta cannot be greater than 1. If you calculate this, that order does not exist. It will mean that the rays of light, theta, is greater than 90 degrees, which of course would not work in this situation. It would mean that the ray of light had come back through the diffraction grating, which is meaningless. Diffraction gratings can be used to analyze the light coming from stars. By finding the wavelength of the light, the temperature of the star and the elements it contains can be found.